In this lesson, we will discuss RSA cryptography. RSA encryption is a public key encryption technology developed by RSA Data Security. The RSA algorithm is based on the difficulty in factoring very large numbers. Based on this principle, the RSA encryption algorithm uses prime factorization as the trapdoor for encryption. Deducing a RSA key, therefore, takes a huge amount of time and processing power. RSA is the standard encryption method for important data, especially data that's transmitted over the internet. RSA is a public key crypto system that MIT professor Ron Rivest, Adi Shamir, and Leonard Adelman invented in 1977. The system is based on several mathematical principles in number theory. Before we dive deeper into RSA, I should note here that several math principles are required to fully understand RSA cryptography. Those mathematical ideas include prime numbers, multiplication versus factorization, greatest common divisor, Euclidean algorithm, relatively prime numbers, modular arithmetic, modular inverse, Euler's theorem, and multiplicative functions. If you are not completely familiar with these concepts, it's okay. You're not the only one. The math behind RSA is really beyond the scope of this course, but I thought I should share this information so you have a frame of reference if you want to do some further research on your own. The RSA algorithm requires key generation, encryption, and decryption. Let's look at some of the math for each. In key generation, we select numbers P and Q, where P and Q are both prime numbers. We calculate n by multiplying P and Q. Also note that in encryption, the ciphertext, capital C, equals capital M to the E multiplied by modulo n. And in decryption, the plaintext, capital M, equals capital C to the D multiplied by modulo n. RSA derives its security from the difficulty of factoring large integers that are product of two large prime numbers. Multiplying these two numbers is easy, but determining the original prime numbers from the total factoring is considered infeasible due to the time it would take, even using today's supercomputers. The public and the private key generation algorithm is the most complex part of RSA cryptography. Two large prime numbers, P and Q, are generated using the Rabin-Miller primality test algorithm. A modulus, n, is calculated by multiplying P and Q. This number is used by both the public and private keys and provides the link between them. Its length, usually expressed in bits, is called the key length. The public key consists of the modulus n and the public exponent, e. The e figure doesn't have to be a secretly selected prime number, as the public key is shared with everyone. The private key consists of the modulus n and the private exponent, d, which is calculated using the extended Euclidean algorithm to find the multiplicative inverse with respect to the totient of n. While the math may sound complicated, an example can really simplify things. Let's look at a simple example. Alice generates her RSA keys by selecting two primes, where P equals 11 and Q equals 13. The modulus, therefore, equals P times Q, which is 143. Therefore, n equals 143. The totient of n phi n, therefore, equals P minus 1 times Q minus 1, which equals to 120. Next, she chooses 7 for her RSA public key, E, and calculates her RSA private key using the extended Euclidean algorithm, which gives her 103. Next, Bob wants to send Alice an encrypted message, capital M, so he obtains her RSA public key, N, E, which in this example is 143 and 7. His plaintext message is just the number 9 and is encrypted into ciphertext, capital C, as follows. Capital M to the E modulo n equals 9 to the 7 modulo 143, which equals 48, which equals capital C. Next, when Alice receives Bob's message, she decrypts it by using her RSA private key, small d and small n, as follows. Capital C to the D modulo n equals 48 to the 103 modulo 143, which equals 9, which equals M. To use RSA keys to digitally sign a message, Alice would create a hash or message digest of her message to Bob, encrypt the hash value with her RSA private key, and add it to the message. Bob can then verify that the message has been sent by Alice and has not been altered by decrypting the hash value with her public key. If this value matches the hash of the original message, then only Alice could have sent it, implying authentication and non-repudiation. And the message is exactly as she wrote, which implies integrity. Alice could, of course, encrypt her message with Bob's RSA public key before sending it to Bob. As discussed earlier, the security of RSA relies on computational difficulty of factoring large integers. As computing power increases and more efficient factoring algorithms are discovered, the ability to factor larger and larger numbers also increases. Encryption strength is directly tied to key size, and doubling key length delivers an exceptional increase in strength, although it does impair performance. RSA keys are typically 1024 or 2048 bits long, but experts believe that 1024-bit keys could be broken in the near future, which is why government and industries are moving to a minimum key length of 2048 bits. Barring an unforeseen breakthrough in quantum computing, it should be many years before longer keys are required, but elliptic curve cryptography is gaining favor with many security experts as an alternative to RSA for implementing public key cryptography. It can create faster, smaller, and more efficient cryptographic keys. Much of today's hardware and software is elliptic curve cryptography ready, and its popularity is likely to grow as it can deliver equivalent security with lower computing power and battery resource usage, making it more suitable for mobile apps than RSA. Finally, a team of researchers, which included Adi Shamir, a co-inventor of RSA, has successfully determined a 4096-bit RSA key using acoustic cryptanalysis. However, any encryption algorithm is vulnerable to this type of attack. So to summarize, here are the RSA key facts. RSA is an asymmetric encryption algorithm with variable length key between 1024 and 4096 bits, and it is considered secure.